Alright, now that we have a clearer understanding of reaction rates, we're going to move into chemical equilibrium. Beginning this, I want to make sure that you understand what is equilibrium. Equilibrium is when the forward and the reverse rate are equal to each other. The forward and the reverse rate are equal to each other. So this is saying that if I have a reaction, okay, so I've got reactants forming products, okay, this is the forward reaction. And at the same time, I have products that are forming reactants. So what we're saying is this is a reversible reaction. Equilibrium is when the rate of the forward reaction, let's say it is 100 reactions per second, is the same as the reverse. There are 100 reactions per second going the opposite way. So what this results in is not, because here's the thing that confuses people, this is not concentrations being equal, not equal concentration, okay? They aren't necessarily equal. In fact, if you take a look at this, notice I've got concentration versus time for the ammonia synthesis reaction. What you notice happening here is I have a decrease and a decrease, so these two must be my reactants. And then this is an increase, so this must be a product. But you notice that you hit this point where they stop changing their concentrations. They stop changing concentrations, and they're going to have a steady concentration, which means that the rate going up and the rate going down are even. They're the same, okay? So at that point, when the forward and the reverse reaction rates are equal, the concentrations do not noticeably change. They really don't. They are going to be changing. They're constantly moving, right? But for every forward that you get, you're going to have a reverse reaction to take its place in that same span of time. And a way that I like to think about that is think of a bridge. Okay, so I've got the Golden Gate Bridge here. You've got, on this particular bridge, you've got travelers going from the city up north, and then from the northbound down to our San Francisco, okay? So San Francisco is here, and let's say these people are traveling to, I don't know, I think it's like San Bruno, one of those cities in Northern California. So San Francisco, I have travelers going northbound, and I have travelers going southbound on the bridge. Well, let's say that the concentration of San Bruno is 100,000 people. And let's say that the concentration of San Francisco is 5 million people. Okay, notice they're not the same populations. What happens on the bridge, though, every single day, let's say I have 20,000 people going north, and I have 20,000 people that go south. At the end of the day, my 100,000 people that I lost are replaced by 20,000 people that I gain, so I still have 100,000 at the end of the day. So the concentration, the population of my city didn't change. The same thing happens with San Francisco. Even though I lost 20,000 people going north, I gained 20,000 going south, so my concentration doesn't change there either. Now, let's take a look at our practice. I'll assume you've paused it and are restarting it now. Chemical equilibrium is when the forward and reverse reactions, I should say the reaction rates are equal. When the rates are equal. The forward rate of a reaction is 100 reactions per minute. The reverse rate of a reaction is 80 reactions per minute. Is this system at equilibrium? Well, since the definition is the forward has to equal the reverse, 80 is not equal to 100, so we would say, no, this system is not at equilibrium. A decomposition reaction has been taking place over the course of 2 days. The concentration of the reactant is 5.23 molar, and the product concentration is 2.16 molar. If these concentrations are unchanging, the system must be, so it doesn't even matter what the concentrations are. It doesn't matter how long this has taken place. All that matters is the concentrations are not changing, so the system must be at equilibrium. Now, draw a vertical line to indicate the point at which equilibrium is reached for the graph below. So the thing we have to think about is concentration, right? So this is molarity, and this will be time. Suppose I should have labeled that. But if this is our concentration, notice changing, 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 but we hit this point where we stop changing. And we stop changing on the other concentration as well. So this vertical line would indicate where equilibrium begins. So past this point in time, the system is at equilibrium.